Welcome to the follow-up video of electric fields. In the first or the previous video we saw that if you have a charged object, there will be an area around the charged object in which an electrical force could exist, provided there is a second charged object. If there is a second charged object, that object will endure an electric force because of that electric field. Now, these electric fields, they come in all different shapes and sizes. We've given you a few examples of this on this page. For instance, if you've got a single point charge represented here by a single charged small metallic sphere that they've put in the center, you will see that there is a radial field that forms around it. Now, how did they create this radial field? Well, this is essentially a type of oil bath, something non-conductive, in which they've put a whole bunch of seeds and grains in there. And those seeds and grains will polarize and will sort of align themselves according to the shape of the electric field around it. Now, if it's a single point charge, it will form this typical type of radial field. If you take 2 point charges, you will get two possibilities, this one or this one. Now, it's impossible to tell what type of charge we took in each of these cases. The only thing we can be sure of is that in situation A, it's an opposite type of charge on both ends. So either this one is positive and this one is negative, or the other way around. We just know that these are opposite charges of roughly the same magnitude. If we wanted to create a field like this, we would have identical charges, either positive or negative, we don't know, but if they repel, this is the type of pattern you get where the field lines are sort of colliding into each other, whereas in this case they're sort of flowing together. Now, the annoying thing about these types of fields is that we of course do not know what type of charge they are, and they are just made by a few grains, like I said, aligning in a certain pattern. Should this be a positive charge, we will have to assume that the field lines, the sense of the field lines, will be pointed away from the charge, which is similar to what we saw when we wanted to draw the field vector. Right? If this one, however, is a negative charge, like so, we would have to assume the field lines are pointed towards it, very similar to what we saw when we were drawing that vector. If we take this exercise, for instance, if I assume this is a negative one, well, this pattern only occurs if both charges are opposite to each other, right? The field lines essentially will be going from the positive charge towards the negative charge, like this. Right, and they'll be pointing towards it here in such a way. Right. Now, let's assume these are both positive in the next example, and what we'll see is that these charges will go sort of upwards and will be pointing away from each other in this case. If they were negative, they would both be going towards them. Now, another interesting type of field is a homogeneous field. Now, the word homogeneous means it's the same all around, and you get that if you combine two flat pieces of metal and you create an electric field between them. How? Well, let's assume the left sheet here is positively charged. The right sheet is negatively charged. We can assume that the field lines are going from the positive towards the negative plate in this case. Roughly, the field vector here is identical, whether you want to draw it here or here. It's an identical field vector, which is the definition of a homogeneous field in essence. Now, if or why do we draw these fields? Like I said here, vector E is easily sketched in different points around those field lines. Why? Well, in this case, all you have to do is take a certain point P and then draw the tangent line in the field lines in that point P. Now this is always a bit of an estimate if you have to do it, because those shapes can be quite irregular every now and then. But if you try to imagine the tangent line there, you will know what the orientation of your field vector E is. If you want to know the sense, well, it follows the sense of the field lines. And as I said, that has to be given. It's away from a positive charge and towards a negative. And the magnitude of E will depend on the magnitude of the charge and the distance between P and the charge in this case. However, you can write this down as well here if you want to. A good estimate can be made by how dense the field lines are. So a good estimate can be made by how dense the field lines are. What do I mean by that? Well, if I scroll back to this situation here, in this area, the field lines are a lot less dense than they are here. Now, the tangent line, if I wanted to know my field vector in this point and in this point, the tangent line is essentially the line that crosses horizontally here, right? Now, do I have to choose left or right? Well, the field line is telling me to go left, so my field vector E would be pointed that way. Now, if I draw it like this, it's a bit of a big vector. A bit too big, maybe, because if I were to draw the situation like this, it would not be correct if these were my field vectors E. Why? Well, the field lines are a lot more dense in this area than they are in this area. So how do I fix this? Well, I just take my eraser and I might make this vector smaller than the one down the center, which makes sense because the field lines are denser around here, right? Similarly, the amount of electric field that you get in the center here, in the exact center, is 0. But it will be a very small field around here, which makes sense because both this charge is making a field vector towards this side, and this charge is making one towards this side. If you add those two up, you're not left with a lot because they have an opposite sense, meaning the electric field here is fairly weak, but it gets stronger as you get towards either of both charges. If I wanted to draw the field vector in this homogeneous field, however, it would have to be equal length no matter where I draw it, because the definition of a homogeneous field is that they're identical no matter where in the field you place point P. Okay? Now, the exercises you have to do are the following. Sketch the vectors in points A and B in the fields below. That's the first bit you'll have to do yourself. Exercise 2. In which point will the vector E have the largest magnitude? And you'll have to choose between A, B, C, or D in this case, with a short explanation as to why you've chosen either answer. Now, exercise 3 is a good old questionnaire. You've got a point P near a charge of 8.3 nanocoulombs, and the electrical field turns out to be 7.2 times 10 to the 6th Newton per Coulomb. How far away is that point P from the center of the charge? If you want to know the exact answer, it is exercise 7 on page 47 in your Dutch book. Now, one final thing that we have to discuss here concerning electrical fields are those inside of a metal object. If you've got a metal sphere like this, right, if it's a simple point charge, there will be an electric field all around it. However, a special thing to remember is if you have a charged object, inside of a charged object, the field is always 0, right? Which means that no matter if you place your point P here to the side or dead center, there will always be no electric field around it. It only starts and will be at its max on the surface of that sphere, right? Which leads us to the next exercise, which graph will be correct given these situations. Now, one thing to remember is there not being an electrical field inside of a metal object, inside of a metal sphere, can be sometimes incredibly handy. Certain cables are able to create electrical fields that can cause disturbances towards other electric machines and components around it. If you put a small or a metal sheet around a cable, you can actually protect that disruptive electric field that is generated from disrupting other objects. A good example of that was in Wales earlier this year, where there was a couple who bought a second-hand TV which had a broken cable. We call these cables coaxial cables. They have the same axis, it's just the inner cable conducts the electricity and the outer cable is just there to protect other electrical devices from any disturbance caused by the electric field of the inner cable. There was a town that had its internet, its broadband internet, knocked out every single day around 7 o'clock in the morning. And why was this? Well, that couple had bought a faulty, a broken second-hand TV, and actually disrupted the entire internet of the whole village every time they turned that TV on, which was always at 7 when they woke up in the morning, of course. And this caused a whole lot of expenses, because they replaced all of the cables inside of that village, just because they did not know that there was somebody using a faulty cable somewhere in the village that knocked it out for everyone else. Right. Little side story, I'll give you a link to that newspaper article as well. Now, you should be able to do exercise 4, 5, and I will be giving you a few other exercises. They will be in Dutch, but you'll find that assignment in your email when you do it. Okay? Good luck with these. If you have any questions, feel free to contact me via email.